What I want to talk about this afternoon is sea level rise, sort of past, present, and future for California, sort of what some of our options are for the future, and I guess we could sum it up with now, certain, and everywhere. If we look at what we know today about sea level rise and what's causing that, the most recent NRC report on sea level rise on the West Coast, our conclusion was ice melt today is responsible for about 2/3 of that, density change or thermal expansion about 1/3, and that's changed over the last several decades. But in any particular location, uplift and subsidence or what the land is doing relative to the ocean is going to affect local or regional sea level. And that's important to keep in mind because we have some real differences across the globe. If we look back, and on the horizontal axis is just the last roughly 350,000 years of sea level rise. As the Earth cools and we go into an ice age, sea level drops. We sequester that water onto the continents as ice sheets. And as the planet warms again, we melt that ice, put the water back in the ocean, and we also expand the water. So we can see about 20,000 years ago, at the end of the last ice age, sea level was roughly 400 feet, 125 meters lower than today. But you can also see that sea level has risen and fallen between some pretty regular intervals. That has to do with some astronomical configurations, roughly 100,000 year cycles with some shorter 40 and 20,000 year cycles in there. But about 20,000 years ago, sea level came back up again relatively quickly in the long-term picture of things. And we can see in a normal pattern, sea level would begin to drop again. It should start to get cooler, but in fact, we know that's not happening. If you just expand that last 20 or so thousand years, we can see when the ice age ended. If we just average out the period from about 18,000 to 8,000 years ago, sea level rose at a rate of roughly ½ an inch a year, 11 millimeters. But in fact, there were periods in there that have been called pulses when it looks like maybe large amounts of ice melted very quickly. We may have seen sea level rise as fast as 3/4 of an inch per year. And then from roughly 8,000 years ago to the last century or so, sea level rose relatively slowly and may not have changed very much at all. Perhaps a millimeter per year or less, but that spans the entire history of human civilization. So during the entire period that civilization has existed, sea level has been essentially constant. So if we look around the world today, we see, villages, mega cities, anything we can imagine in terms of infrastructure development was built quite close to sea level. Today, if we look at the most recent numbers, we're seeing sea level rise of 3.2 millimeters per year, roughly 12 inches per century, so we can see that's a significant increase. But in fact, in all likelihood, the way things are moving, that rate is probably going to increase as everything else seems to be increasing. There are some temporal differences in sea level. The rate of change, what we just talked about with periods of glaciation or glacials and interglacials, sea level can change over millimeters per year, but over hundreds of feet, over thousands of years. Those are things we're thinking a lot about today. We also have large-term changes in plate tectonics where ocean basins and ocean ridges can change their configurations. Those aren't really affecting us in a big way today, but that can happen over millions of years. And then we have short-term changes. And those are things I want to focus a bit on because I think in the short term, those are going to be of much greater concern than whether sea level is rising at 3.2 millimeters or 3.3 millimeters per year. Tsunamis, not a huge issue for the California coast. We do have them occasionally, where water can rise 10 to 20 feet over minutes. Storm surges, which Patrick will talk about next, of up to 3 feet or so over hours. El Nino, which appears to be on the way. We can see an elevated sea level of a foot or two that may take place over months. And then the tides, which we know the ranges on the California coast pretty well, 8, 10, 12 feet maximum, but now we have king tides, which may add a few more inches on top of that. So the NRC did a report a couple of years ago, was asked to respond to requests by governors of the 3 western states on past, present, future sea level rise and select the best values for 2030, 2050, and 2100. This is sort of a summary of sea level rise from roughly 1800, where it didn't change a whole lot up until perhaps 1900. Those values are based more on geological evidence, what we see deposited along shorelines and coastlines. Over the last century or so, using tide gauges from around the world, the average has been put together at about 1.7 millimeters per year. One of the challenges, each of those tide gauges is local or relative, and it's a function of what land mass it's hitting on. So whether that number was perfectly accurate based on where most of the global tide gauges are relative to the distribution of land masses is still sort of a question. But we got rid of that local influence beginning in 1993 by launching a couple of satellites that are now measuring, basically using lasers from space, looking at the sea surface. That number now has nearly doubled. But I think a really interesting question is, how do you measure sea level from several hundred miles up in space down to tenths of a millimeter per year? How do we do that? But then, as I often say, I don't know how a cell phone works either. But to me, that's really amazing technology, because we know exactly where those satellites are because somebody told us where it was. But if you look out into the future, we can see a couple of colored bands there. One is model projections, and we have lots of different models with lots of different inputs for the various parameters in those models. So we get a range of values. As you see, as we go from 2050 to 2100, that range gets larger. And then we have empirical models coming mainly from Vermeer and Ramsdorff, who have looked at into the geologic past and looked at what general global temperatures were and what sea level was, and made some connections between those two. So rather than a model that looks at all the different parameters, that sort of integrates all those together. But what is important is, by the time we get out to 2100, there's a pretty big range. And if one was a director of public works or the head of a utility company and wondering about what sea level rise estimate to use, clearly the further out you go into the future, the more the uncertainty. And I sort of liken this to somebody who's just gotten out of college and is now trying to plan how much to save for retirement 40 years into the future. Well, what's a property going to cost? What's food going to cost? What's anything going to cost? And there's a lot of uncertainties. With climate and sea level, there's a lot of uncertainties. In fact, I use one of my favorite climatologists. There's the known knowns, there's the known unknowns, and the unknown unknowns. So some of the things that we've been dealing with are greenhouse gas emissions. Does any of us know what the CO2 content of the atmosphere will be in 2100? A lot of people like to know that. So those are some of the uncertainties, cloud cover, permafrost thawing, that all go into that number in the future. So it's not that scientists don't know what we're doing. We just don't know what society is going to do. So those ranges try to incorporate all the uncertainties. Some of the big uncertainties, and we see a lot about this, are what's going to happen with the ice, because that's sort of the 800-pound gorilla. All the mountain glaciers in the world, if they were to melt from Patagonia and the Himalayas and the Alps, maybe 2 feet of sea level rise equivalent. Greenland, if it all melted, roughly 22 feet of sea level rise equivalent. And Antarctica is the big one at roughly 200 feet. So we've got maybe 225 feet of sea level rise if everything melted. Nobody thinks that's going to happen in the near future, and it's interesting, here we are 85 miles inland from the Golden Gate. But Sacramento is only 30 feet above sea level. But many people know, and many do not, that Sacramento is actually a port. We have the port of West Sacramento, and we have the port of Stockton. So sea level comes up to Sacramento. So it's not just what's happening on the open coast. It's anything within a few feet of sea level. So these are uncertainties that we're trying to figure out. So how do we turn that ice melt off? A lot of people are trying to understand Antarctica, what's happened as these ice shelves break down, and then these ice sheets start to move quickly. This is to see if you're awake slide. So we took the numbers, or I took the numbers from the NRC report to try to put those in a context people can understand. So this is for the year 2030, and there's the low estimate we came up with, the midpoint, which is about 6 inches, and the high point. So this is only 15 years into the future. Remember, the last century was about 7 or 8 inches globally. By 2050, the midpoint in our estimates was about 12 inches, and the high point was 24 inches. And by 2100, we could be somewhere between 16, roughly 3 feet or a meter is our midpoint estimate, and it could be, sorry, Danny, 65 inches. So there's a big range, and depending on where we are and how close we are to sea level, we're going to see greater or lesser effects. And some people would even say we should be looking at higher numbers, and there's those that are thinking these might be too high. So if we just look at San Francisco, we can see things like, this is from the old DC site, and they've modified this now and hooked up with Climate Central. But you can see with a 16-inch sea level rise, which is possible by mid-century or shortly after, maybe shortly before, San Francisco International Airport runway begins to go underwater. And this is just on the lower right is just happens to be the Oracle building, which is in an area that would actually start to go underwater. So San Francisco Bay margins are much more exposed in many ways to these gradual sea level rise extremes in areas on the open coast. So the point I want to make is sea level rise is increasing slowly. The bathtub is slowly overflowing, but it's going to be the extreme events that are going to cause us greater concern in the near term. This is just a picture from Mission Beach in San Diego in a storm in 1988. Looks like a nice place to buy a house. There's a nice wide beach. In fact, there's even a concrete seawall at the back of the beach. I know those houses are probably pretty cheap in San Diego. Maybe $2 million, $3 million, I don't know, but it looks like a good investment. The next picture is taken from right there during this event in 1988. So the beach is gone, the water is going over that wall, and every time I see this picture, I try to figure out what these people are doing. I think one might be a realtor selling the house. El Nino, again, can elevate sea levels a foot or two above normal. This is Redwood City inside the bay in the 1997-98 El Nino, and you can see the red line is the predicted high tide, and the blue is what actually happened. So we had 2 feet of additional sea level beyond what was predicted. And if you think about the present sea level rise rate of 12 inches per century, that's 200 years of sea level rise that one El Nino brought on for several months. So these short-term events are going to be really important. We've now begun to identify king tides when the tides are at their extreme several times a year. This is in Mill Valley, actually one of the on-ramps to the freeway there. So there's a number of things that we're going to see with both these short and long-term increases. Flooded roadways, inundated park facilities, oceanfront home damage, and also cliff retreats. The more hours of high tide and the higher the tide gets, the waves are going to attack the cliffs more frequently. Cliff retreat will increase. So another way of showing those short-term events is to look at the San Francisco tide gauge, and we can see this goes back to the oldest one in the country, back to about 1855, and see this gradual increase. And you can see some big past El Ninos, which showed 11 or 12 inches of short-term rise. What's also interesting is over the last 10 or 15 or so years, people have recognized that sea level sort of leveled off. But if you look at it now, I don't know what this means, but all the tide gauges along the west coast are now have gone up about 6 inches in the last several years. I don't know what that means. But we may have changed to another regime of some sort. So which future projection should we be using at any one site? Well, what's the closest gauge tell us? What's the closest tide gauge tell us? What's the cost or value of the project or the infrastructure that we're thinking about? What's the lifespan? And what's the impact of losing it? So is it a pathway, a parking lot, a desal plant, a sewage treatment plant? Those are going to have a big impact on what we select. We can look at across the country, again, because of relative sea level rise, and see some real differences. Interestingly, some of the lowest rates tend to be on the West Coast, where we seem to be the most concerned. Washington, D.C. is not particularly concerned. They have a high rate. And when we look at a lot of these others, they're in states and places where we don't even use the word sea level rise. So a little bit on resilience. There's a lot of thought now on how we can make resilient communities and coastlines. First, there's a big difference between the East Coast, where we have mangroves and marshes and coral reefs, which may not work for the California coast for a number of reasons. Almost 60% of the California coast looks like this: low bluffs with marine terraces. Can we make that resilient? Steep rocky cliffs, another 13%, and then these low-lying sandy, dune, beach, estuary coastlines. My question is, how do we make each of these resilient, or can we? So I think what we need to do is inventory all those areas that are subject to short and long-term sea level rise. What are the vulnerabilities, and then how do we begin to respond or adapt to that? We did some work in the city of Santa Barbara and tried to look at the most recent LIDAR elevations, which at least begins to give you a sense of what features are how close to sea level. And we looked out 50 years and 100 years. But the important thing on any of those maps that are now out there on the internet is how good is the topography that they're using to project 1 foot or 2 feet or 5 feet into the future. So options for the future, we can scare the heck out of everybody. Probably not very effective, but there are places where that is probably not too far from reality. This is Japan, Hurricane Sandy. We can do the engineering approach: massive dikes, massive flood walls. Places where we've done this in the past, but I think they're having second thoughts about how far into the future they can continue that approach. Armor. Personally, I think the days of armor and new armor are probably past. 33% of the Southern California coast has been armored, but that's not the direction we're going any longer. For a while, that will work, but there's going to be an endpoint. Houseboats and floating cities. How many people can afford to live in places like this? I think it may not work. We can use planned retreat. These are both East Coast pictures. Or we can do unplanned retreat. And we're starting to see more of that taking place. And Ocean Beaches may be a good example of where we're planning a retreat path that's been agreed upon. So I'm going to leave you with 5 two-word sentences that wrap this up. We have exactly enough time if we start now. It's real. It's bad. It's us. Scientists agree. And there's hope. Thank you.